In this section, we're going to be focusing on the calculus of vector-valued functions. In the last section, we talked about what a vector-valued function was and how it relates to a space curve. We started with the limits of vector-valued functions in section 3.1. In section 3.2, we want to continue that study of the calculus of vector-valued functions by following a similar path to the one we took when studying real valued functions of a single variable in Calculus 1. First, we're going to define the derivative, look at some applications of the derivative, and then we'll move on to defining integrals. We're going to discover some interesting new ideas along the way as we do this, and some interesting properties of space curves. As part of the work that we're going to do in this section, we'll need to define what we mean by a smooth curve, and we'll learn to describe the tangent vector to a space curve at a specific point. We'll also describe the unit tangent vector, which is the tangent vector divided by its magnitude. Now, the last thing that we'll talk about in this area is the tangent line, which goes through a point. Remember, the line continues in both directions. And so we have the tangent line, the tangent vector at a point, and we also have the unit tangent vector. Let's go ahead and take a look at our learning objectives for this particular section. We want to be able to write the expression for the derivative of a vector-valued function. We want to find the tangent vector at a given point for a given position vector. Find the unit tangent vector, which would just be dividing the tangent vector by its magnitude at a given point. And then we want to explain what the significance of that unit tangent vector is. And finally, we want to calculate the definite integral of a vector-valued function. Let me share my screen with you and we'll get started. The first thing we want to talk about is the derivative. Now, the derivative of a vector-valued function is nearly identical to the derivative of a real valued function of one variable. However, remember that the input to a vector-valued function, while they are real numbers, some parameter t, the output is a vector in either 2 dimensions or 3 dimensions. And when you connect the endpoints, the terminal points of all those vectors, you get a plane curve in 2 dimensions and a space curve in 3 dimensions. So when you take the derivative of this vector-valued function, it makes sense that the derivative would also be a vector. For a vector-valued function, the derivative actually gives a tangent vector to the curve represented by the function at any given point. So the derivative is actually the tangent vector. Let's go ahead and introduce the more formal definition of the derivative now. Again, this is probably not the one that you're going to use on a daily basis to calculate the derivative, but it is similar to what we saw in Calculus 1 with the definition of the derivative. It's basically the same. The derivative of a vector-valued function r of t, r prime of t, is the limit as delta t goes to 0 of the vector-valued function evaluated at t plus delta t, moving over a little bit, minus r of t, all divided by delta t. This sounds exactly like the difference quotient that we saw in Calculus 1. Now, this is true provided the limit exists, then it is what we say differentiable at t. If the derivative for the vector-valued function r of t exists for all t in an open interval, say between a and b, then we say that r is differentiable over the interval a to b. For the function to be differentiable over a closed interval, we have to add a couple of conditions. The following 2 limits have to exist as well. So it has to be differentiable over the open and differentiable coming from the right at the left endpoint and coming from the left at the right endpoint. In other words, the one-sided limits have to exist at A and at B for it to be differentiable over a closed interval. Now that is the formal definition, but what's the practical definition? What do you really do when you want to find the derivative of a vector valued function r of t? Whether it is a function in 2 dimensions or 3 dimensions, remember that it consists of real valued functions multiplied by the unit vectors, I hat, j hat, and k hat. So in order to find the derivative of the vector valued function, we just take the derivative of those real valued functions still multiplied by the unit vectors. So this would give us f prime of t, g prime of t in 2 dimensions, and the vector f prime of t, g prime of t, and h prime of t in 3 dimensions. The component functions f, g, and h have to be differentiable functions of t. If they're not differentiable, then r of t is not differentiable. Let's take a look now at example 1 and 2. We'll just do both of them together. In example 1, we want to find the derivative of the vector valued function, and it is a 3-dimension vector because it has an I hat, j hat, and k hat component. To find the derivative, it literally just means take the derivative of each component function, but remember that it is itself a vector. So this is going to give me another vector valued function, the derivative of 3t squared in the I hat direction, 2e to the 2t in the j hat direction, and negative sine of t in the k hat direction, right? So literally all I did was take the derivative of the component functions, but kept it in vector form. This is another vector valued function. This is the tangent vector to the vector r of t, given at any value of the parameter t. Now let's do the same thing for this second example, and we'll go ahead and do that now. It's a little bit more complicated because the component functions are more complicated. The derivative of natural log is 1 over the argument times the derivative of the argument, which in this case would be 3t squared. Then the derivative of the second term, or the second component, has 2 terms. The derivative of e to the negative t is negative e to the t, but the second term in the second component is a product. So you're going to have to use product rule. Now, since you have to use product rule, it may be more advantageous for you to factor out the e to the minus t before you do the derivative. So you could compute the derivative with respect to t of e to the minus t times 1 minus t. And then, of course, the derivative of 0 is still 0, so that one is done. And then I can apply the product rule because this is a real valued function, just like if it was in calculus 1. So the derivative is the same as it was in calculus 1. So when I take the derivative now, I've got to apply the product rule. So the first term does not change and the third component does not change, but the middle component, I have to take the derivative. So the derivative of e to the negative t is negative e to the negative t. So I have negative e to the negative t, still multiplied by the second component unchanged, that's f prime g, plus g prime f. So the derivative of the factor 1 minus t would be a negative 1, so minus, and then times the first factor, e to the minus t. And then I have a 0. And then you've got some algebra to clean up here. Notice that you do still have 2 terms, and they're separated here by this subtraction that's out in the open, not the one buried inside parentheses. They both have an e to the minus t. In fact, they both have a minus e to the minus t. And so you could go ahead and factor out that minus e to the minus t, which I will do now, which would give us minus e to the minus t times 1 minus t plus 1. Note that when you take out the negative, it changes that last sign to a positive. which it looks like that gives me 2 minus t. And so my final answer, or what I would want to see on an exam, is 3t squared over t cubed plus 1 negative e to the minus t times 2 minus t, comma 0. It is, again, a vector valued function. The derivative of a vector valued function is another vector valued function. And this represents the tangent vector, not the unit tangent vector, but the tangent vector. Let's now talk about some of the properties of the derivative, right? Most of the facts that we know about derivatives from Calculus 1 still hold. In particular, the constant multiple rule, the sum and difference rules, the product rule, the chain rule, these all extend to vector valued functions. The one that is a little weird, as you might expect, is the product rule. And the reason for that is because we have more than one type of product with vectors. We have dot products and we have cross products. And we could also have a product with a scalar as well. So we have multiple ones. So there are 3 extensions in the case of the product rule: a real valued function multiplied by a vector valued function. So you might take an r of t, which is a vector valued function, and multiply it by an f of t, which is a real valued function. So when you're doing that, that's one kind of product. So you've got this, well, real valued function times a vector valued function. Then you could do the dot product of 2 vector valued functions, or the cross product of 2 vector valued functions. And the product rule is going to have to be applied to all 3 of these in slightly different ways. So we're going to start by letting r and u be differentiable vector valued functions of t. And we're going to let f be a differentiable real valued function of t. So f of t is like an f of t from college algebra or calculus 1, right? Just a regular old function of t, not a vector value, just a real one. Put in a real, get out a real. And we're going to let c be a scalar. So the scalar multiple rule says that if you want to take the derivative of a constant times a vector valued function, you could pull the constant out and then do the derivative of the vector valued function. This is exactly the same as calculus 1. The sum and difference rules tell us that if we have 2 vector valued functions either added or subtracted together, we could add or subtract them first, then do the derivative, or we could take the derivative first and then add or subtract them. This is exactly the same, again, as calculus 1. Then we have a scalar valued function, a real valued function, multiplied by a vector valued function. So this is f of t, no harpoon or arrow above the f, multiplied by r of t, which is a vector valued function. So f of t spits out real constants, and r of t spits out vectors. Notice that when you apply this, you get essentially the same thing you would have gotten if you'd done the product rule in calculus 1. So you have the derivative of the first times the second plus the derivative of the second times the first. Notice the order is different, though, from what we do in calculus 1. Now, because this is commutative, it doesn't really matter. I could have written it as r prime t times f of t. I didn't because I'm preparing you for the cross product. So what I'm preparing you for is to always have the first factor written first, because when we get to the cross product, it's going to matter. It doesn't actually matter here, and it won't matter for the dot product, but it does matter for the cross product. The dot product is, again, very similar, just pretty much the same as what we would have done in calculus 1. It's the derivative of the first factor multiplied by the second, plus the derivative of the second factor multiplied by the first. Again, the dot product is commutative, so I could reverse the order of this and write u prime of t times r of t. It would be exactly the same thing. The one that is not exactly the same is the cross product. When I look at the cross product is not commutative. And the rule for the product rule of the cross product is that r prime of t gets crossed with u of t, so derivative of the first crossed with the second, plus the first again crossed with the derivative of the second. You know that the cross product is not commutative. If you get these backwards, it's going to have the wrong sign. It will be opposite in sign to what it should be. So it's the first one written first in both cases. So those are our three different product rules that we see there. And then we've got the chain rule, and we've got the dot product of a vector with itself. So the chain rule says, what if I put a real valued function in place of the parameter t inside of a vector valued function? How do I take the derivative of a composition? Well, it's pretty much still just the chain rule that we've seen before. Derivative of the outside, don't change the inside, times the derivative of the inside, where the derivative of the inside is a real valued function, right? This last rule is an interesting one. It says if I have a vector valued function and I dot it with itself and I get a constant, then the dot product of the vector with its tangent vector will be the scalar 0, all right? So if I dot a vector valued function with itself and I get any constant at all, then the dot product of the vector with its derivative will give me 0. All right. Now, remember, this caution is about the way that we typically in Calculus 1 wrote the product rule. We typically wrote f prime g plus g prime f. But in the cross product, it has to be written f prime g plus f g prime. All right? It doesn't matter for the dot product, and it doesn't matter for the product of a real valued function with a vector valued function, but it does matter for the cross product. Let's now take a look at example 3. So we're going to look at example 3 several different ways, all right? So we're going to use some of the properties, and we're also just going to calculate it directly. So the first thing I want you to do is simply to take r of t, which is right here, cosine of t for the I hat direction, sine of t for the j hat direction, negative e to the 2t power for the k hat direction. And I want you to compute the derivative of r. And then I want you to take the dot product of r with r prime. So just calculating it directly, not using any of the rules that we see up above. So go ahead and pause the video while you work it out, then turn the video back on so we can compare. Okay, so let's compare how we did. When we're looking at this one, the first thing I did was I computed r prime of t, which gave me the vector negative sine of t, comma, cosine t, comma, negative 2e to the 2t power. Then I went ahead and did the dot product of the two vectors together. Remember, the dot product gives you a scalar, not a vector. It gave me a negative cosine t sine t plus cosine t sine t, which those canceled each other out, plus 2e to the 4t. Since the bases are the same, you add the powers. 2t plus 2t gives you 4t. Then this gives you 2e to the 4t. Finally, to compute the derivative of it, I simply take the derivative with respect to t of 2e to the 4t, which led to 8e to the 4t power. Now let's go ahead and reevaluate exactly the same thing, but instead, let's use the formula that was in number 4 up above, the property that the derivative of a dot product is the derivative of the first dot the second plus the derivative of the second dot the first. All right, so let's go ahead and apply that now to our r of t dot r prime of t. Now, taking and applying the property would give us the derivative of the first, so r prime of t, dotted with the second, which is also r prime of t, plus the first as is r of t dotted with the derivative of the second, but the derivative of the derivative is the second derivative, which gives us r double prime of t. Go ahead now, you already have r prime of t, so you can compute r double prime of t, and then apply the formula that you see there, and we'll compare our answers and see if we again get 8e to the 4t power. Pause the video now while you work it out. Okay, so let's take a look. We needed to compute the second derivative of r, which gives us negative cosine of t, negative sine of t, negative 4e to the 2t. Then to apply the formula from the property, we need to dot the first derivative with itself. And I did that here in blue. When you dot the first derivative with itself, you get sine squared plus cosine squared, which will give you a 1, plus, and it looks like I've lost my plus somehow, plus 4e to the 4t. Remember, when the bases are the same, you add the powers. So you get 4e to the 4t. Then you want to add to that the dot product of the original vector valued function r of t with its second derivative. And I did that here in this pink colored. So when we take the dot product of r with r double prime, we get a negative cosine squared of t minus sine squared of t. If you factor out the negative 1, you get cosine squared plus sine squared, which is 1, times the negative 1 gives you a negative 1. And then the product of the third components gives you a positive 4e to the 4t. So you have a 1 and a negative 1, which cancel. And these are both like terms, both e to the 4t terms. And 4 plus 4 gives us 8, which does match what we found directly. You'll notice that I don't really think that this is easier. Whether it's easier or not depends on the particular vectors that you have. You'll simply have to judge whether you want to do it by direct calculation or using one of the properties. Let's now take a look at the second part to this example, which is to compute u of t crossed with r of t. We want to do this first by direct calculation, and then we'll apply the formula that we found in example number 5 in the properties. So the first thing we need to do, of course, is the cross product. These are vector valued functions. So remember, you have to find the determinant of a sort of 3 by 3 matrix where you have I, J, and K as row 1. You can either expand by a row or column, or you can repeat columns 1 and 2 and use the multiplying factors method. Go ahead and pause the video while you work it out, then turn it back on so we can compare. Okay, this one is a doozy. This is not a pleasant problem. So notice that I really spread out the pseudo determinant of the 3 by 3. It's a pseudo determinant because I, J, and K are not scalars. In fact, none of these are scalars. They're functions and vectors. So it's not exactly a matrix, but it acts like one, so we treat it like one. I chose to repeat columns 1 and 2 because I didn't have any 0 elements. When I worked this out, I did the major diagonals in blue and I did the minor diagonals in pink. So I took the products of the major diagonals from upper left to lower right, and then I subtracted the minor diagonals from upper right to lower left. Then I went ahead and combined the I hat components and got negative e to the 2t sine of t minus sine t cosine t in the I hat direction. I got cosine squared t plus t e to the 2t in the j hat direction. T sine of t minus sine t cosine t in the k hat direction. Then I had to take the derivative of all of that. All right. Now, I knew that I was going to have to do product rule no matter what, but several of these had product rule in more than one term, but they did have a common factor. So in the I hat and in the K hat components, I first factored out the common factor, which would make taking the derivative simpler and simply require one application of the product rule and not two. So then I worked out the applications of the product rule in this last triple line that you see here at the bottom. And let me scroll that up a little bit. So the first of the three lines is the derivative of the I hat component, which gives us cosine t times the quantity negative e to the 2t minus cosine t, plus sine of t times the quantity negative 2e to the 2t plus sine of t. All of that makes the I hat component. The j hat component, I didn't need to apply the product rule in the first term, but I did need chain rule. So I got negative 2 cosine t sine t. And then I got, for the second term, plus e to the 2t plus 2t e to the 2t from the product rule in the second term. And all of that gave me the j hat component. And then I have the last component by applying the product rule to sine of t times t minus cosine t, which gave me cosine t times t minus cosine t plus sine t times the combination 1 plus sine t. Now, that is nasty, right? I mean, that is extremely nasty. Let's see if it's any better if we apply the formula that came out of number 5 in the properties of the derivatives of vector valued functions. So we want to repeat the process and hopefully come up with the same answer when we take the derivative of u crossed with r. But this time we want to apply the property that you see here. So the first thing I recommend you do is that you rewrite what r and u are, and then write down what their derivatives are. Then you have to compute two separate cross products, and then you have to combine together their result. If you want to, go ahead and pause the video, work it out, and then turn the video back on, and we'll compare our results. Okay, if you thought the last one was bad, this one probably drove you nuts. So my recommendation is that you simply pause the video for a while and make sure that you can follow everything that's on the screen. So I took the cross product of each side individually, and then I simplified each side, the I hat, j hat, and k hat components. And then I added the two together, because when we do u cross r, we get two cross products added together. And then we have to take the derivative of that. So first I got those separately, then I added them together, which you'll see here in the pink. I was then simplifying out to the right, a couple of them to simplify the derivative by taking out a greatest common factor. And then I apply the derivative to this step, and I come up with the final here. With the exception of the last line, they're exactly equal to what we had in the first time that we did this by direct calculation. The last line, you have to use some trig substitutions and identities in order to get them to be equivalent. I think that the purpose of all of this is just to get you used to applying the properties and used to the cross products and dot products and working with vector valued functions. The rest of this section will not be nearly so difficult. Let's go on now and let's take a look at what we mean by a smooth curve. Now, most of the time when we talk about a curve being smooth, we have a sort of gut feeling for what that means. It basically means no pointy or jagged pieces in it. But what do we say about that curve in 2 or 3 dimensions to make it precise? In 2 dimensions in the plane, it means that it was continuous, except possibly at the endpoints of an interval, and it was differentiable. So to be smooth in calculus 1 meant that the function itself was continuous, all right, draw it without picking up your pen, and it was differentiable, which meant it had no corners, no cusps, and no vertical tangent lines, and that made it smooth. Their definition in 3D is somewhat similar. When we're talking about in 3D, we want the function r of t to be continuous, which again means that it exists at the point, that the limit of it exists at the point, and the two point to the same thing. And we don't want the derivative to be the zero vector for any value of t except possibly at the endpoints of the interval, again allowing maybe for it not to be continuous or whatever at the endpoints. So an example would be a helix or a slinky. If you think about the slinky is smooth, right? There's no pointy parts to it. So we have a good idea of what we mean if we're looking at a picture. It's a little bit more complicated to make it mathematically precise. But again, in 3 dimensions, that means that r of t, the vector valued function, is continuous, and the derivative of it is not the zero vector, which basically means it has a tangent vector that points in a given direction. All right, if the tangent vector was the zero vector, it doesn't point anywhere and it points everywhere. All right, so when we look at these two pictures, the one on the right is not smooth because it has a cusp and a corner in it. And the one on the left is, well, smooth, right? No pointy parts. We're now ready to switch gears and talk about integration of vector valued functions. So we'll start, much like we did with derivatives, with the formal definitions and then how we actually do it in practice. So just as we did before, we're going to take a look at how do we find the antiderivative of a vector valued function. Now it's going to turn out that the fundamental theorem of calculus still applies to vector valued functions, which makes our work much simpler. If we think of a vector valued function as representing the velocity of an object at a point in time, then its antiderivative would represent position. Or if the function represented the acceleration vector at any point in time, then the antiderivative would represent its velocity. Same relationship that we saw in Calculus 1. The derivative of position is velocity. The antiderivative of velocity is position. Let's now take a look at the definition of the integral of a vector valued function. So we're going to start in the two-dimensional case with a two-dimensional vector valued function, r of t, given by f of t in the I hat direction and g of t in the j hat direction. In order to integrate this vector valued function, we integrate the real valued function in the component that is in the I hat direction, f of t dt, and leave it in the I hat component. Then we integrate the real valued function g of t, which was in the j hat component, and we leave it in the j hat component. We need to add a constant because this is an indefinite integral, but this time, because our derivative is a vector valued function, our constant has to be a constant vector. So our c isn't just a constant scalar, it is instead a constant vector of the same dimensions. So this will be a two-dimensional constant vector. We have a very similar definition for 3 dimensions, which you can see right here, the indefinite integral. You simply take the indefinite integral of all 3 components and add on a constant vector. Now, what if you want to do a definite integral? If you do a definite integral using the fundamental theorem of calculus, you know that you want to evaluate it at the 2 endpoints, and you don't have that constant vector added on. So to do this, we take the definite integral of f of t, the definite integral of g of t, and leave them in vector form. And this will give us the definite integral of a 2-dimensional vector valued function. And we have a very similar definition down here for the 3-dimensional case, which you can see here. So all we need to do is integrate the individual components, just as when we did the derivative, we took the derivative of the individual components. Let's go ahead and take a look at example 4. In example 4, what we want to do is we want to go ahead and evaluate a definite integral from t equal 1 to t equal 3. We have a vector valued function indicated by the presence of the standard unit vectors I hat and j hat. So this is in two-dimensional space, or the plane. In order to compute this, what we're actually going to compute is going to be the vector valued function, which is the integral from 1 to 3 of 2t plus 4 dt for the I hat component, and the integral from 1 to 3 of 3t squared minus 4t dt in the j hat component. Go ahead and pause the video, work it out, and tell me what you get. So this one is much simpler than the ones we did before when we were working with the properties of the derivative. You simply integrate the two real valued definite integrals, and you get 16 for the first and 10 for the second. So the integral of the vector valued function is the vector 16, 10. The next thing we want to do is we want to talk about tangent vectors. I don't know why there's so much space there. So we want to go on and talk about tangent vectors and unit tangent vectors. So when we talk about tangent vectors as opposed to unit tangent vectors, the tangent vector is the derivative of a vector valued function. So if I'm looking for the derivative at the ordered triple 1, 4, 3, then the tangent vector would be the vector tangent to the space curve at that point. It would have both a direction and a magnitude. Now, the unit tangent vector would point in the same direction, but would be magnitude 1 long. So the difference between the tangent vector and the unit tangent vector is the magnitude. Now let's reconsider the graph of the vector function r of t from the last section, where r of t is 2 cosine t, 2 sine t, and 3, a 3-component vector valued function. Now, we know, based on what we've learned in this section, that r prime of t would be negative 2 sine of t for the I hat component, 2 cosine t for the j hat component, and 0 for the k hat component. If we let t be the value pi over 4, then we can find the value of the vector valued function r of t at pi over 4. So going back to the original, the cosine of pi over 4 square root of 2 over 2 multiplied by 2 would just give me square root of 2. And then the sine of pi over 4 is also square root of 2 over 2 multiplied by 2 would give me another square root of 2. And there's no place to plug it in the third component, so it stays 3. So I have a point that is on the space curve for the vector valued function r of t. I also know what the tangent vector is at that point. It's negative 2 sine t, 2 cosine t, and 0. Now, the derivative at this point, then, if we substitute in the value of t as pi over 4, substituting it into r prime of t, would give us negative square root of 2, square root of 2, and 0. And if we were to find the magnitude of this, we would square each one and get 2. 2 plus 2 would give us 4, and then we'd take the square root, so it has magnitude of 2. So let's take a look at what it looks like in the picture. So coming down here, again, this was a circle graphed in the plane where z equals 3, parallel to the xy plane. And we're looking at the point, which is pictured here in pink. And you can see coming off of it the black tangent vector. And the length of that black tangent vector is 2, and it's extending from the point. Now, the unit tangent vector would be half that length, a length of 1. And CalcPlot3D typically plots it in a sort of purple color. All right, let's take a look now at what this one looks like out here in Calc Plot 3D. So you can see it right here. You can see it coming off. And I've plotted the point, which is right here. And notice that in order to get the square root, I raised it to the 0.5 power. You can also spell out SQRT and open parentheses to do that as well. And you can see that I plotted R of t right here. Now, if you click in here and you want to see the unit tangent or the tangent vector, notice that what I have clicked is velocity vector. Calcplot 3D calls the tangent vector the velocity vector because if the vector valued function is position, the derivative of it is velocity. So it calls the first derivative the velocity vector. The second derivative would be the acceleration vector. If I want to see the unit tangent, I can click this box down here, which says show unit tangent. So if I come down here and click this, it should show up on the graph. And then if I come over here, maybe I need to hit enter to get it to recalculate, or maybe turn it a little bit. I think it's kind of hidden because of what I have out there. So let me, oh, I didn't indicate at what value of t. The value of t I was using was pi divided by 4. So that's the problem. So let's do pi divided by 4 and hit enter. And now you can see it. All right. So it's kind of hard to see. But if you look closely, you'll see this little purple arrow sticking out there. Right. That's the unit tangent vector lining up with the tangent vector. And if you want to see it better, come out here and take off the velocity vector. And then when you take off the velocity vector, we may have to reevaluate to get it to go. Looks like it's a little hung up right now. It's not wanting to show without the velocity vector. All right, so we'll just have to leave the velocity vector and the unit tangent vector on there. Okay, let's now talk about terminology. All right, let's define it a little more specifically. Basically, starting with a vector valued function, r of t, the derivative is the tangent vector, r prime of t, provided it exists and it's not the zero vector. If it's the zero vector, then it's not really tangent to the curve because it has magnitude of 0 and points in all directions and no directions. It's called the velocity vector in Calcplot 3D, and it's plotted in black. This is different from the unit tangent vector. Let's look at that one down here. The unit tangent vector takes the tangent vector, r prime of t, and divides by its magnitude so that it has length of precisely 1. So you can see over here in this picture a little bit better the purple unit tangent vector and the black tangent vector. Notice the tangent vector is slightly longer, indicating that it has magnitude greater than 1. Let's now take a look at the tangent line. What's the tangent line? Well, the tangent line would go through that point, but it would extend in both directions forever. So it's not coming off in the direction of motion. Right? If the original graph is the position, the tangent vector comes off in the direction that the object was moving as the t value increases from the minimum to the maximum. The tangent line, on the other hand, goes in both directions, doesn't have an orientation. To find the equation of the tangent line, we need to take the position vector of the point where they're meeting, which I believe ours was square root of 2, square root of 2, 3. And that will be our x naught, y naught, z naught. And then we want to add that position vector to the derivative vector at point P multiplied by a parameter t. The parameter t is what's going to make it go in both directions forever. All right, so that would give us something like this here. Okay, so let's take a look now at a unit tangent vector and the tangent vector. So what I have plotted right now, and I'm going to move it around a little bit. Right now it's at the point 2. Let's move it around a little bit. Do you see how it's tracing out the curve at all points, if I had it facing the same direction, that unit tangent vector would always be the same length. It looks like it's growing and shrinking because of the three-dimensional element of the graphing in CalcPlot 3D. But in fact, it's always a length of 1. All right. Let's take a look at these two visualizations of that same curve, one when t equals 2 and one when t equals 5.15. So when t equals 2, it's right here at this point, pictured in black, and here is my unit tangent vector. And coming over here at this one, I can see at 5.15, it's right here. So I have this length to it. So let's take a look at the same thing, but let's add the velocity vector back onto the graph. So let's make sure that the velocity vector is graphing, which it is not. So let's put it on, and now I can see it. All right, and I want this at 2. So I'm just going to hit 2 and hit enter. So notice that in this particular picture, the velocity vector is just barely longer than the unit tangent vector. So the velocity vector is not very large, as opposed to when I look at 5.15. So 5.15, when I do that one, notice that the tangent vector in black here sticks out further than the unit tangent vector, which tells me that the velocity, the magnitude, which is speed, is greater when t is 5.15 than it is when t is 2. It's moving faster at that point in time than it was moving earlier. And here are the two positions with the velocity vectors graph, so you can tell the difference. So you can tell it's barely longer than the unit vector when t is 2, and quite a bit longer when t equals 5.15. Now we have one last example we want to work. We want to find the general formula for the tangent vector, and then find the unit tangent vector to the curve given by the vector valued function t squared plus 1 for the I hat, 3 minus t for j hat, and t cubed for k hat. So this is in 3 dimensions. And then we want to find the vector equation of the tangent line. All right, so the first thing we want to do is come up with the tangent vector. So in order to find the tangent vector, we simply take the derivative. So when we take the derivative, let me see, where can I write? The tangent vector r prime of t is going to be given by 2t minus 1 and 3t squared. All I'm doing is taking the derivative. Now this is the derivative. Now I want to take this tangent vector, which is a vector valued function representing the velocity if the original was position, and I want to turn it into a unit vector. So I want it exactly 1 unit long. So I lose the information about speed, but I still have the direction information. So in order to do that, I need to divide by the magnitude of this vector. So let's go ahead and find the magnitude of that vector first. So when we find the magnitude of the vector, this is the square root of each component squared. So I have 2t squared plus -1 squared plus 3t squared quantity squared, which is going to give me 4t squared, all under the radical again, plus 1 plus 9t to the 4th. Now, there's really no way to simplify that. You can't add terms, they're not alike. You can't factor anything out because you've got that constant there. So there's really not anything that you can do with that, all right? You're pretty much stuck with 9t to the 4th plus 4t squared plus 1 if you want to put it in descending order. So how do I turn this tangent vector into a unit tangent vector? Well, you just take each one of these components and divide by that mass. And that will get you the unit tangent vector. I didn't say it would be pretty. I just said it was possible. For the unit tangent vector, we use an uppercase letter T. That does not represent the tangent vector. It represents unit tangent vector. So the unit tangent vector is going to be 2t divided by the square root of 9t to the fourth plus 4t squared plus 1, comma, -1 divided by the square root of 9t to the fourth plus 4t squared plus 1, comma, 3t squared divided by the square root of 9t to the fourth plus 4t squared plus 1, right? The unit tangent vector will be used for quite a few things later in the course. You'll see where it's coming out, part of it in the next section that we study, which is motion in three-dimensional space. The last thing we wanted to do was come up with an equation, a vector equation for the tangent line at the point t equal 1. If we're going to do that, I need to know what the original point is on the space curve when t equals 1. So in order to do that, I need to come back to the original and find r of 1. So I'm going to go ahead and do that up here in gray font. So I have r of 1, which is going to be equal to 1 squared plus 1, 3 minus 1 for the j hat, and 1 cubed for k hat, which gives me the vector 2, 2, 1. All right, that's a position vector. So the point is 2, 2, 1 in round parentheses. The position vector with the initial point at the origin and the end point at that ordered triple is vector 2, 2, 1. So I'm going to take that vector 2, 2, 1, and I need to add to it a direction, and the direction needs to be in the direction of the tangent vector or the unit tangent vector. You can use either the tangent vector or the unit tangent vector to represent your point. It could be either one. Now, obviously, the unit tangent vector is more complicated. So in this case, I would probably just use the tangent vector. But I want the tangent vector specifically when t is equal to 1. So I'm going to come up here and I'm going to find r prime of 1, which is going to give me 2, -1, and 3 as a vector direction. All right, so this is my direction. So in order to get the vector equation of the line, what I do is I take my position vector of the point. So this is my tangent line when t equals 1. And I'm going to take the point that is the vector position, which is going to be 2, 2, 1, and add to it all possible multiples of 2, -1, 3, right? Now, I could also have used the unit tangent vector, in which case I would have needed to divide the 2, the 1, and the 3, 2, -1, and 3 by 9 plus 4 plus 10, the square root of 14, all right? So I could have had that as well. But since t is varying from -infinity to infinity, it's going to graph out the whole line in both directions. Let's go ahead and take a look at what this one looks like. So here's the curve right here. And you can see that the curve is sort of multicolored right here in different colors. If you want, I can make it a solid color so it stands out a little better. Come up, use constant. No, I don't want the same color. Let's make it purple. Okay, so now it's purple. The tangent line is in that gold color. The blue arrow is the position vector of the point when t equals 1. The purple vector, the short one that you see here, is the unit tangent vector pointing in that direction. And the longer black one, which you can barely see the tip of it here, that is the tangent vector that we found, which I think was 2, -1, 3 or something like that. So when you're looking at this, this is giving you the tangent line. And notice that we entered the tangent line as the position vector 2, 2, 1 plus t multiples of the direction vector 2, -1, 3, which gives us x of t is 2 plus 2t, y of t is t minus 2, and z of t as 1 plus 3t. And we allow t to go from -infinity to infinity. But this is the end of this particular section, 3.2, talking about the calculus of vector valued functions. I hope that you now have a lot more experience and feel more comfortable with it. In the next section, we'll be talking about some applications of the calculus that we've learned with vector valued functions. Namely, we'll be looking at arc length and curvature of a space curve or a plane curve. I hope you'll join me for the next section, 3.3.